Let us derive an expression for the relationship between ionic conductance and ionic mobility. Ionic conductance is directly proportional to ionic mobility, or lambda I, that equals a constant into ionic mobility, and this constant is Faraday, and this can be proved as follows. Consider a dilute solution of an electrolyte taken in a cubic vessel of 1 meter cube volume, and this solution is in between two electrodes having unit area. Let the applied potential difference between the two electrolytes be 1 volt, so that the potential gradient is 1 volt per meter. The current passing through the solution is given by Ohm's law, that equals I equals E by R, and in this case, as E equals 1, we can write that equals 1 by R, and that is C, conductance in Ohm raised to minus 1. And since we have taken the electrolyte solution in unit volume, the measured current will be same as the specific conductance, because specific conductance, it is the conducting power of all ions in unit volume. And we know the relationship between equivalent conductance and specific conductance, that is equivalent conductance that equals specific conductance divided by C, or the specific conductance that equals equivalent conductance into C. And in this case, since the solution is very dilute, you can take the equivalent conductance as equivalent conductance at infinite dilution. Then we know at infinite dilution, the equivalent conductance will be the sum of the ionic equivalent conductance according to Kohlrausch's law. So that is lambda 0 cation plus lambda 0 anion, that into C. That is according to Kohlrausch's law. Where lambda plus 0 and lambda minus 0 are the ionic equivalent conductance at infinite dilution. Then the quantity of electricity Q, that equals I into T. And since the current is passing through the solution in 1 second, you can write Q equals I, so that is lambda plus 0 plus lambda minus 0 into C. Now, let the limiting ionic mobility of the cation and anion be U plus 0 and U minus 0. And we know ionic mobility equals speed of the ion or divided by potential gradient, or the distance traveled by the ion in unit second divided by potential gradient. And in this case, the potential gradient is unity, and in unit time, ionic mobility changes to distance, or we can say in unit time, all cations within this distance u plus meter get discharged at the cathode, and all anions within the distance u minus gets discharged at the anode. And since the area of the electrode is 1 meter square, we can say all cations within the volume u plus 0 meter cube and all anions within the volume u minus 0 meter cube will get discharged at the respective electrodes. And so that number of gram equivalents of cations carried by the current of cathode will be equal to C into U plus 0. This is because there are C gram equivalents per meter cube. So in U plus 0 meter cube, the number of gram equivalents present will be C into U plus 0. Or the total number of gram equivalents of ions, total number of gram equivalents of ions transported will be equal to C into U plus 0 plus U minus 0. We know the charge carried by 1 gram equivalent of ions is equal to 1 Faraday. Therefore, the total charge carried by C into U plus 0 plus U minus 0 gram equivalents will be Q, that equals F into C into U plus 0 plus U minus 0. We have already seen that Q equals C into lambda plus 0 plus lambda minus 0. And if you equate these two, we get F into U plus 0 plus U minus 0, that equals lambda plus 0 plus lambda minus 0. And comparing similar terms on both sides, we can write F into U plus 0 equals lambda plus 0 and F into U minus 0 equals lambda minus 0. Or we have U plus 0, that is ionic mobility at infinite dilution, that is given by the expression lambda plus 0 divided by F, and U minus 0, that equals lambda minus 0 divided by F. Or in general, you can write U I for a given ion at infinite dilution. The ionic mobility is given by the expression lambda I0 divided by F. And if you consider a weak electrolyte where alpha is the degree of dissociation, you can write ionic mobility as lambda I equals, Ui equals lambda I divided by alpha into F, where alpha is the degree of dissociation. And this is the case for weak electrolytes.